Hello everyone, we are still in week 1 of the first quarter of this school year and we are going to continue our lesson on sequence. Let's enjoy today's lesson. Lesson 1.2, Sequence as a Function and its Explicit Formula. So by the end of this lesson, you will be able to write the terms of a sequence given the functional relation f of n. You will be able to generate patterns and write the explicit formula for the end term of a sequence. Note that a sequence is also defined as a function whose domain is the set of natural numbers or a subset of consecutive positive integers. So for these examples, we will use the functional relation where n is a natural number to write the first four terms of the sequence described. So f of n is equal to 2n minus 3 described a sequence. Let's look for the first four terms. Solving for the first four terms, meaning our n consists of 1, 2, 3, and 4. 1 denotes the first position, 2 denotes the second position, 3 denotes the third position, and 4 denotes the fourth position. So, to solve for the first term, you replace n with 1, and this will be equal to negative 1. To solve for the second term of the sequence, replace n with 2, and that will give you 1. Next, for the third term, substitute 3 to n. You will have the third term, 3. And the fourth term is 5. So therefore, the sequence is negative 1, 1, 3, and 5. Next, f of n is equal to negative 3n plus 8. Again, our domain, 1, 2, 3, 4. So, f of 1 is equal to negative 1 times 3 plus 8. Simplifying it, it will give you 5. For second term, replace n with 2, and your second term now is 2. For the third term, replace n with 3, and the third term is negative 1. For the fourth term, substitute 4 to every n in the functional relation, you will get negative 4. Therefore, the sequence is 5, 2, negative 1, negative 4. For our third example, f of n is equal to 5n minus 4, where our domain consists of 1, 2, 3, and 4. So solve for the first term, it's f of 1 is equal to 5 times 1 minus 4. And that will give you 1. Next, for the second term, substitute 2 to every n in the function, and that will give you 6. For the third term, substitute 3 to every n, it will give you 11. For the fourth term, substitute 4 to every n, and that will give you 16. I hope you have mastered your integers because that is really big, because that will be a big help in simplifying all this. Okay, so the sequence is 1, 6, 11, 16. For our fourth example, we have a rational expression on the right side of the function. F of n is equal to 8n all over quantity n plus 12. So again, we will use the domain as 1, 2, 3, 4. So substitute 1 to every n in the function to get the first term. That's 8 over 13. To get the second term, substitute 2 to every n. And simplify. For this case, I simplified the numerator, I simplified the denominator, but ended up not having a lowest term. So we have to reduce this to lowest term. How do we do that? Correct. We need to divide it by the greatest common factor of both the numerator and denominator. And the greatest common factor or greatest common monomial is 2. So it will give you 8 over 7. 8 over 7 is an improper fraction, and you can convert it to mixed form. And that is 1 and 1 over 7. The third term is the same process, substitute 3 to every n, but this time I prefer not to multiply the numerator. I prefer to factor out the denominator because I don't want to get my numbers bigger. So we need to factor 15 such that it will have a greatest common factor, or it will have the same factor in the numerator at least. So 15 is factorable as 5 times 3, and it will have the same factor in the numerator. Therefore, I can cancel this one out because they are equal to 1. I will be left with 8 over 5, and that is an improper fraction again. I will convert it to mixed form, and that is 1 and 3/5. The reason that I convert improper fraction to mixed form is that it is easier for me to see which one is greater than the other. I can easily observe if the numbers is increasing or decreasing. Next, f of 4 refers to the fourth term, and that is 2. Therefore, the sequence is 8 over 13, 8 over 7, 8 over 5, 2. Or 8 over 13, 1 and 1 over 7, 1 and 3/5, 2. For uniformity of our answer, please use the mixed fraction of the sequence in case you have an improper fraction. Okay, thank you for following that. Hope so. Okay, example number 5. F of n is equal to negative 3, the quantity of negative 3 raised to the quantity of n minus 1. Replace n with 1 to get the first term. So f of n is equal to the quantity of negative 3 raised to 0. A number raised to 0 using the loss of exponent, the zero exponent. It tells you that if a base is raised to 0, then it is equal to 1. For this case, the entire negative 3 is the base with an exponent of 0. Therefore, it is equal to 1. But if the case is this, negative 3 without a parenthesis raised to 0 is equal to, this is equal to negative 1. Why? Because the only base of 0 exponent here is 3. Negative is not a base of 0. Therefore, you have negative 1 times 3 raised to 0. So, you have to simplify 3 raised to 0, that is 1, times negative, so that's negative 1. So, when you use your calculator, make sure you use the parentheses if you intend to say that the entire expression will be raised to 0. So, f of 1 is equal to 1. For the second term, replace n with 2, and it will give you f of 2 is equal to the quantity of negative 3 raised to 1, which is negative 3. For the third term, replace n with 3, and you simplify it as the quantity of negative 3 squared. But, wait, you have a negative base, and you have an even exponent. So, it tells you that by the general knowledge that negative expression raised to even exponent is always positive. So, example, negative times negative, that's a positive. So, for example, you have 4. Negative times negative is positive times negative is negative times negative is positive. Okay? So, this one is positive 9. Negative times negative is positive. 3 times 3 is 9. Okay, next for the fourth term, it will be negative 3 raised to 3. Negative base raised to n tells you that it will be and it will always be negative. Negative base raised to add is always negative. So when you have negative 1 raised to 1001, then that is negative. Okay? So for this one, it's negative 27. Therefore, the sequence is 1, negative 3, 9, negative 27. Okay? But sometimes, listing all the terms of a sequence can be slow and difficult to do. Just like when you solve for the number of hits on the website at the end of the month, you would be required to list down the 31 terms of the sequence. So, to make it easier, there is an efficient way to determine a specific term. If you intend to get the 31st term, you can easily get that particular term without listing everything before it. So, that is using the formula. So, we have to write a sequence using a formula. Okay, let's recall. A sequence is a function whose domain is a set of natural numbers or a subset of consecutive positive integers. Therefore, it is clear in our mind that when we use the functional relation, our domain n is a natural number. Okay, that's functional relation. It is also an ordered list of numbers or elements like geometric objects that often follow a specific pattern or function. That's why it should hold for all, because it is a pattern. Every term is meaning every individual number or element in a sequence. That is what we call term. We have a functional relation in our previous example. So f of n is equal to negative 3n plus 85. The first few terms are 1, 6, 11, 16, and so on. The sequence with n term, if you express this having the n term, 1 can be written as a sub 1, 6 can be written as a sub 2, 11 is written as a sub 3, 16 is written as a sub 4. The subscript is actually the domain. It tells you the position of the term. That's why the subscript here is 1 because this is the first term. The subscript here is 2 because this is the second term. The subscript here is 3 because this is the third term, and so on. This a sub n is the assumed last term. We don't know the exact value of this, but we call it as the a sub n. Whatever number that is, it is a sub n. It is always the last term. So we will relate the function to the formula of a sequence. The functional notation f of n is actually the same as a sub n. So for this example, it could be written as negative 3n plus 8 is equal to a sub n. Okay? So this f of n came from here, and it is equal to a sub n. To write it more appealing, it's a sub n is equal to negative 3n plus 8. Okay? Therefore, if we want to know the 31st term of this sequence, we don't have to list down everything here. All we have to do is to substitute 31 to n, since we are looking for the 31st position. So a sub 31 is equal to negative 3 times 31 plus 8, and that is negative 85. See, it's easier compared to listing everything. That's the beauty of knowing how to get an explicit formula. But what is an explicit formula? Explicit formula defines the terms of a sequence using their position in the sequence. So example, let's write the explicit formula of the given sequence. 10, 15, 20, 25, 30, 35, and so on. So we will try to write 10 using the position. The position is 1. So how do you get 10 from 1? You simply multiply them, right? So 10 is equal to 1 times 10. Your second term is 15. How do you get 15 when your position is 2? If you put 2 here, since we're generating a pattern, if you place 2 here, it will be 20. So it would be too long. You need only 15. So you make it 2 times 5, that is 10, plus 5. Okay? You see the importance of this plus 5? Where did we get this? Where did we get the idea that we have the plus 5 here? Or that this is the number that we're going to add, aside from knowing that this could give you 15 when added. Okay, correct. The difference between two consecutive terms here is 5. So that puts into your mind that 5 there is very important. Okay? But this one is a pattern for the second term. Let's see if it will hold for the first term. So let's try to express 10 having the position times 5 plus 5, because we only want to keep the position and the rest of the numbers there. Indeed, it is possible. First position times 5 is 5 plus 5 is 10. How about the third, 20, and your position is 3. So 20 is equal to 3 times 5 is 15 plus 5, correct? Observe that it follows the same pattern. It holds for all the given terms. Therefore, we can conclude that your functional relation is f of n is equal to n times 5 plus 5. F of n is equal to 5n plus 5. And your explicit formula then is a sub n is equal to 5n plus 5. Easy? Yes. Next, 6, 16, 26, 36, and so on. Observe if there is something that you can use in observing the pattern or forming the formula. Okay, let's try to use it. The position is 1, so 1 times 6, that will give you 6. 16 is equal to position times 6, that's 12. You need to get 16, so you add 4. But if you will do the same thing with the first given, it will not hold. Therefore, your first assumption is not correct. Next, to try, let's use both n, the position, and the 10, which is actually the common gap or common difference between the terms. So 6 is actually equal to 1 times 10 minus 4. 1 position, 10 is the difference here. Then since it's 10 and you need to get 6, you subtract 4. Can you follow? Okay, next. For the second term, that is 16, and your position is 2. 2 times 10 minus 4. Is this equal to 16? Yes. So it holds on the first and on the second term. On the third term, it still holds. So 3 times 10 is equal to 30 minus 4, 26. So it holds that formula. So with the next term, so f of n is equal to n times 10 minus 4. F of n is equal to 10n minus 4. And the explicit formula is a sub n is equal to 10n minus 4. Okay? Next, 1, 4, 9, 16, and so on. Again, our n will be 1, 2, 3, 4, up to n. Observe the pattern. Notice that the difference between terms is not the same. That means we cannot use the previous solutions that we had where we observed the common difference between two consecutive terms. Since we are going to use the position of the term and looking at the terms, you will see that The first observation that you will see is that 1, 4, 9, 16 are all perfect squares, right? 1 is a perfect square as 1 squared. 4 is a perfect square with 2 squared. 9 is a perfect square with 3 squared. 16 is a perfect square with 4 squared. And if you think of it, the base that I mentioned, 1, 2, 3, 4, are all the position or the end. So you can simply say that your function is equal to n squared, and your explicit formula is a sub n is equal to n squared. Good job! Next. This is somewhat similar to the previous example. Notice that in this sequence, all the numerators is 2. All the denominators are factors of 5. This is 5. This is 5 times 5. This is 5 times 25 or 5 times 5 times 5. This is 5 times 125 or 5 times 5 times 5 times 5. Therefore, you can see that it will be expressed in exponential as to this one. And looking at the exponents of the denominator, it actually refers to the first position, second position, third position, fourth position, and so on. Therefore, your explicit formula is a sub n is equal to 2 over 5 raised to n. Easy. Next. 1, 5, 25, 125, and so on. Look at the given sequence. Somewhat similar to the previous, but this time, all these denominators are now numerators or are whole number already, including 1. Can you again think of a pattern relating each term to its position? Okay, you will see that 1 is the same as 5 raised to 0. This is 5 raised to 1, 5 raised to 2, 5 raised to 3. And that 1 means you only subtract 1 from the position. So, 5 raised to 1 minus 1. This is the position. 5 raised to 2 position minus 1, and so forth. Therefore, it's 5 squared, 5 raised to 0, 5 raised to 1, 5 raised to 2, 5 raised to 3, and can be simplified as explicit formula a sub n is equal to 5 raised to the quantity n minus 1. Okay? It's your turn. Write the explicit formula for the nth term of each sequence. I will give you 1 minute. Okay, so I hope you get the correct answer. The answer is a sub n is equal to negative n cubed. If in case you place parentheses here, I will accept that. But next time, in this particular sequence, Parenthesis is not necessary since the signs did not change. Okay, next for this one, a sub n is equal to n times n minus 1, which can be simplified as a sub n is equal to n squared minus n. Okay, so I hope you enjoy our class and I hope you learned something. So for this week, we have assignment number 1, the introduction to sequence. So this is also posted in our Google Classroom. Upload your handwritten solutions and answers. So the instruction there is you solve this on your notebook, take a picture of it, then save it as PDF, and then attach it to your assignment, and then don't forget to click turn in. Okay, so that would be all for today. Thank you. Stay safe. God bless. Bye.